Hi, I'm Alfonso Lagares, a student in Professor Fenton's Physics 2211 class, and this is my Lab 5 report where I'll be studying the motion of a skydiving jump. First, I'll introduce the concept of aerodynamic drag and how the drag force on objects moving through a fluid can be calculated. I'll then move on to describing the real skydiving jump that we'll be studying today, followed by the explanations and analysis of the models created to understand this jump. I will finally present the conclusions found using these models. For this lab, I chose to study the motion of a free-falling skydiver. During fall, the only two forces acting on the skydiver are the force of gravity and the force of aerodynamic drag. The latter force is caused by the constant collision of air particles against the area of the skydiver exposed to the airflow and is dependent on a number of variables. The force is proportional to the square of the velocity, the area of the skydiver that is perpendicular to the velocity and is thus exposed to the majority of the collisions against their molecules, and proportional to the density of air. The force is also dependent on the shape and geometry of the object, but this relationship is hard to characterize. All these effects are thus combined into a coefficient, the coefficient of drag, which accounts for the shape of the object falling and must be found experimentally. Some of these variables, like air density, are not constant in the atmosphere, but instead vary with height. In order to gain a better prediction of the trajectory of the skydiver, this change in air density must be accounted for. The standard US atmosphere is a lookup table with values for density, temperature, and gravitational acceleration given a certain altitude. This table was used to calculate the force of drag acting on the skydiver throughout its trajectory. I will be trying to model the record-breaking jump performed by Felix Baumgartner and the Red Bull Stratus team. The jump started at a height of 36,402.6 meters and reached a maximum velocity of 377.1 meters per second. Felix was traveling at a supersonic speed for 30 seconds through the flight, and he opened his parachute at 1,521 meters above the ground. In order to compare and evaluate the different approximations we made to understand the motion of the skydiver, I created four models that implement multiple interpretations of the problem at hand. The first model only calculates the force of gravity on the skydiver, assuming that gravitational acceleration is constant for all heights. The second model calculates both the force of gravity and the force of drag, assuming the gravitational acceleration and air density at sea level are constant. The third model accounted for both forces but looked up the value of air density and gravitational acceleration as a function of height along the motion. Finally, a fourth model increased the area of the skydiver when its height reached the parachute deployment altitude in order to simulate parachute deployment and its effects on trajectory. The code was not included due to its extension, but it can be found on the link found in the description. After running the different simulations, the position and velocity of the skydiver were calculated. The first and second models serve as a lower and upper bound for the trajectory of the skydiver. For the more accurate prediction, we can see that the third and fourth models predict an initial acceleration similar to the first model, meaning that for high altitudes, the force of drag is not extremely significant. After reaching around 7,500 meters, the density of air and the speed become significant enough to start slowing down the fall. Velocity starts to decrease as the terminal velocity of the skydiver decreases until the parachute is deployed, at which point the velocity of the skydiver drops significantly. This velocity is maintained until the ground is reached. Calculating the speed of sound in air throughout the trajectory and comparing it with the speed of the skydiver, we can see that Felix was traveling faster than the speed of sound for around 30 seconds during the initial stages of the jump. He was able to accelerate through the thinner, less dense part of the atmosphere and pick up speed to break the sound barrier, but when he reached the thicker lower atmosphere, this velocity was lost to drag. For our model, this means that our approximations were valid, as the model was able to accurately predict the maximum velocity and period of supersonic flight the skydiver experienced. However, the model failed to predict accurately the motion during the deployment of the parachute. As this acceleration graph shows, the model predicted incredibly high accelerations when the parachute deployed, going as high as 500 meters per second squared. This would have definitely killed the skydiver, but as that did not happen, our assumptions must be incorrect. I believe that a better approximation to the real behavior of the skydiver would have been to increase his area continuously over time after the expected height of deployment, as the parachute does not open instantly, and thus the area changes as a function of time. This would smooth out the accelerations found in the model, bringing them closer to the ones found in real life.